Welcome back, everyone. I'm absolutely thrilled to be hosting this explainer today on behalf of Forge College. In our last session, we got the lay of the land with our ERC-3643 security token overview and looked at the broader Solana context. Today, we're diving into something super practical and honestly pretty fun, mapping ERC-3643 features to Solana primitives. We're basically going to take those Ethereum concepts we learned, pack them up, and successfully dock them right here on Solana shores. It's time to translate the rules and get ready to build. Okay, let's take a quick look at the blueprint for today. We've got Welcome to Solana Shores, Manifest, Captain, Port Rules, Mapping Fields to Primitives, the Mapping Descriptor Prototype, Bridging the Feature Gaps, and finally, wrapping up the blueprint. Lots to cover, so let's dive right in. First up, Section 1. Welcome to Solana Shores, from concept to code. Moving right along to Section 2, Manifest, Captain, Port Rules, the shipping analogy. So to actually build an ERC-3643 token on Solana, we need a really solid mental model to translate these abstract concepts into real functioning code. Think of your token as a ship. On the EVM side, the identity concept is basically your shipping manifest. It clearly describes the cargo. The authority is the captain steering the ship, and the policy dictates the strict local port rules. Now on Solana, these translate beautifully. That manifest, it becomes discoverable metadata accounts. Our captain, that maps to a PDA. And those port rules are strictly enforced by our compliance accounts. It's like a giant puzzle, and the pieces fit together surprisingly well. Let's pause for a second on that middle piece, the PDA, or Program-Derived Address. This is quite literally your token's digital ship captain. On Solana, you're going to want to lean heavily on PDAs whenever you need a program-controlled, revocable role. Why? Because a PDA has absolutely no exposed private keys for anyone to lose or compromise. This means the token program can securely and trustlessly verify role authority right there on-chain. It's the perfect captain, one that never sleeps, never takes a bribe, and always follows the rules. All right, Section 3, Mapping Fields to Primitives, the Engineering Matrix. Now, what's really interesting here is how we act as the harbor master, mapping specific EVM semantics directly to exact Solana constructs. Take the issuer field, for example. That maps perfectly to a mint authority PDA, keeping the program firmly in control. Then you've got the controller role, which translates to a PDA authority account equipped with role flags. This is how we build in that crucial revocability. And what about those vital transfer restrictions? Well, they become dedicated compliance accounts, think allowlists or denylists, paired up with Token 2022 freeze capabilities to really enforce those port rules. Continuing with our matrix, let's talk about general metadata. We map this to a small on-chain metadata account, but we pair it with an off-chain URI. Why do it this way? Well, storing a massive PDF prospectus on-chain is going to cost you an absolute fortune in Solana rent. So we keep the heavy lifting off-chain and only store the cryptographic verification hashes on-chain. It's just smart engineering. Finally, transfer hooks translate directly to compliance program instructions. These get called automatically during a transfer to enforce mandatory things like KYC checks. Next up, Section 4, the Mapping Descriptor Prototype, our translation engine. Okay, so we've got our mapping matrix, but we really need to automate this process with a mechanical translation engine. Enter the mapping descriptor. We built this using a TypeScript prototype, and this deterministic object is the ultimate bridge between the two ecosystems. It essentially takes your standard ERC-3643 style JSON and outputs a perfectly structured Solana-focused object. It preps all the PDA seeds, account names, and metadata hashes entirely off-chain. That way, when you go to initialize everything on-chain, it's smooth, it's predictable, and it's totally auditable, a real game changer. The whole process is actually elegantly simple. Step 1, you just input your standard ERC-3643 JSON. Step 2, the engine goes to work generating deterministic PDS seeds, like appending a unique issuer ID to a base seed string, for instance. And step 3, it spits out the final mapping descriptor. The real beauty here is that we are calculating all of this complex state completely off-chain. This frees up your Solana program to do what it does best: instantly validate and enforce the rules without getting bogged down. Now, because this descriptor is literally the foundation of our entire security token, unit testing is absolutely not negotiable. So what should our tests actually look for? Well, first, we need to verify that for the exact same metadata, the derived PDA seeds always map to the exact expected PDA addresses. Second, we have to confirm that our allowlist entries are perfectly preserved during the translation. And third, we must ensure that identical inputs always produce completely deterministic outputs. If your descriptor passes these checks, you know it's behaving exactly as engineered. Moving into Section 5, bridging the feature gaps when one-to-one fails. So the crucial point here is that moving from the EVM to the SVM isn't always a perfect one-to-one translation. Sometimes, you're trying to fit a square Ethereum peg into a round Solana hole. To bridge these feature gaps, we use three main strategies. First, we aggressively leverage Token 2022 extensions for things like transfer fees or confidential transfers. Second, when Token 2022 doesn't quite have what we need, we build small custom compliance programs that hook into the process. And third, we have to carefully choose how we handle heavy storage items, like massive allowlists. And speaking of allowlists, this brings up a major engineering trade-off you'll need to make. On one hand, you can store your allowlist as separate explicit accounts. This approach is incredibly simple and highly auditable, but man, it carries a steep storage cost on-chain. Alternatively, you could pack all those entries into Merkle roots stored in a single compact account. This drastically reduces your rent costs, by a lot. But it does add a layer of complexity because you have to handle cryptographic proofs during transfer validation. You really have to weigh what makes the most sense for your specific protocol. Finally, Section 6, wrapping up the blueprint. Next steps. We have covered an immense amount of ground today and successfully drafted our engineering blueprint. As we step toward actually writing our on-chain code in the next phase, let's lock in some core design principles. Always preserve the true behavior semantics. Map what a feature means, not just what it looks like. Prefer program-controlled PDAs for all your revocable authorities. Keep that large, bulky metadata off-chain and just store the hashes. And meticulously document and unit test any of those feature gaps we talked about. So, I'll leave you with this thought. Are you ready to finalize your PDA seeds, pick your allowlist storage method, and start building out your test fixtures? Because the groundwork is officially laid, the harbor is fully prepared, and it is almost time to start writing the actual on-chain enforcement logic. Thank you so much for joining me for this explainer. I really hope this structured look at mapping ERC-3643 to Solana primitives has made the complex seem, totally manageable. If you want to dive deeper into this subject and explore a ton of other amazing Web3 topics, I highly encourage you to visit forge.college to keep learning and start building. On behalf of Forge College, thanks for watching. Until next time, happy coding.